Yeah, Piped Courier Tacit. It's about functional programming. I only have 10 minutes, so I'll move quick. My name is Abbe Keultjes. I work at Frontmen. It's my avatar, my name, and my email. There's nothing more to it. Let's get started. So my goal of this presentation is that I'd like to write that I like that people write more declarative code, more declarative than they do now. And you might ask, what is declarative code? I think there's a yeah, I had to hide the thumbnails. I think there's a gradient between imperative on the left and then declarative code on the right. Code can either be imperative or declarative or something in between. And to explain what it is, I've thought of a few pointers. Imperative code is concerned with how, and declarative code is concerned with what. So imperative code is more concerned with how things should work and how a feature or a function should behave or do its intended functionality. And declarative code is more concerned with with the end result, with what it should do or what it should be, maybe. Imperative code tends to have more implementation details, and declarative code is more abstract. It has more abstractions. This also means that declarative isn't better than imperative code per se. I think in most cases it is. In a lot of cases it is better, but not always, because abstractions have to have their costs, and too much abstraction is not good. And finally, imperative code requires reading, often, not always. But imperative code tends to be more. It tends to be more code, so you have to read more, and also you have to read more code to understand what it does. And declarative code requires knowledge. You may need to read less than imperative code, but because it works more with abstractions, you need to know. You need to know those abstractions. So there's a trade-off. I'd like to show some examples of code. By the way, this presentation has a lot of code. I hope it won't frighten you guys, but bear with me, please. So first, a very imperative piece of code. It's the end result of the code is, as you start with an array of numbers and maybe a falsy values, and the idea is that it's going to convert those numbers into a string in the end. These numbers can be passed to a string from char code, which return the corresponding character. And in this case, I've chosen the result shit because I think it's shitty code. Like I said, it's very imperative. There's a lot of implementation details, a lot of code. Also, you need to read a lot of lines to see what it does. So I don't like. If I see this code in the code base, I would be well, a little bit scared maybe. This piece of code is already a lot better. It's already a lot more declarative. It does the same thing. It also converts an array of numbers to a string. It uses the array prototype methods, filter, map, and join in this case. But still, it's not as declarative as it can be. Oh yeah, it can be. I think it can be better. It's not. I mean, it's not the worst code. It's fine if I see this code in the code base. It's okay. But the goal of my presentation of this lightning talk is I would like to convince you. I hope to convince you that it can be even better than this. Like so, this is an example. It still does the same thing. The data is different. In this case, it outputs nice as the word, because I think it's nice. It uses it's similar to the array prototype methods you saw before, but in this case it uses some functional programming functions like pipe, reject, map. Map is basically the same, but it's more functional. It doesn't use any prototype or objects. And then finally, there's maybe I hope it's an example where to show that something can be too declarative maybe. So it relies, in my opinion, too much on abstractions. And like I said before, this declarative code requires knowledge instead of reading. So in this case, you have to know what over means and lens prop and ASOC. This might be a little bit difficult, and maybe it's too declarative. Maybe it's not. Yeah, it can be better. Yeah. So now I want to show you guys a few examples of how to make regular kind of imperative code, how to make it more declarative. And here come the three words in the title of my presentation: pipe, query, and tacit come into play. And I want to start with some bit of starting code, and I want to convert it slowly into more declarative functional code. So to start, we're going to create a unicorn from a horse. So our input is a horse and our output is a unicorn. Well, we all know how to make a unicorn from a horse. It's not that hard. We take a horse, we paint it white. We attach a horn to its head, and we feed it some magic stuff, a rainbow and sprinkly magic stuff, and we return it, and we get a unicorn. It's not very imperative code. I think it's easy to read, but I chose a simple example to keep the examples that are coming hopefully easier to understand. I also want to show you the end result. So this is where we're going. I hope it's easier to read. It uses the pipe function we saw before. It's just one line, but still it's not too difficult to see what's happening. So how do we get from the starting code to the end result? First, I'd like to introduce the pipe function. It's let me first say the code is going to be a lot worse. First, it's going to be a lot more code. It's going to get harder to understand. I think the pipe function is pretty hard to understand actually. But I believe it's one of the most used utility functions in functional programming. So that's why I added it to my presentation. This is the signature of the pipe function. It's a function basically that accepts one or more functions, and each of these functions transforms your input. And the input is in this case A. I've called it A, and the output is B. Just the names I gave. So it's a function that accepts functions. It returns again a function that accepts the input, and finally it returns the output. So you can use Lambda or Lodash/fp to they supply a pipe function. You can also make it yourself. It's not that hard. But in this case, I imported from Lambda. So here we're going to use the same function. We're going to make a unicorn from a horse. So we have the same function as before. It takes a horse, and then inside the function we call pipe. We're going to pass it a couple of functions we'll see soon, and we are immediately passing horse as the input to pipe. So each function we supply to pipe, we have to, because they take two parameters, in this case the paint and the thing we want to paint. We need to wrap each function in a wrapper function, because the pipe only supplies the input we supply it. The same for the second function. So in this case, we receive the white horse, the painted horse, and in the final function we receive the horned white horse, which we only have to feed it the magic stuff, and finally it returns the unicorn. I hope this is clear to you guys. If not, please tell me later. I'll try to explain it more if I can. So the second thing is querying. this might be, well, it's also it's also pretty difficult, I think. Not to, yeah, it's difficult to explain, and it requires some what's the word, some practice to wrap your head around it. The thing with currying, it's when you have a function, that's in this case our paint function, and it takes two parameters or two arguments, and to curry this function, we have to make a function that receives each parameter and then returns a function that receives the next parameter just until we've gathered all the parameters. So in this case, we have two parameters, so we need to wrap it. You could say wrap it in two functions. So the current version of Paint, it first accepts the color parameter. It returns a function that accepts the thing parameter, and again that returns a function that calls our initial Paint function. This is currying. It's sort of so to speak wrapping functions until you have functions that each take one parameter until you have gathered all parameters. We'll do the same for the attach function. It also has two parameters, so again it's the same thing, to gathering functions, so to speak. Feed, or our feed function, has three parameters, so we have to do one more time, one more extra wrapping. And then we have the same thing as before. We have the unicorn function, which takes the horse. We still have pipe, and now we can pass, instead of like we saw before, instead of doing these awkward wrapping stuff where we, yeah, it's actually more imperative, I think. Now we can do. We have somewhat clean code. We call each function. We call it with the first parameter, and so calling this function with our first parameter, with the white paint in this case, it returns the next function in line. So when pipe passes the horse to this function, it passes the horse to here, yeah, that will finally call paint and attach and feed, and we have our unicorn. Finally, we can do one more thing to make it better, to make it more declarative, because we've actually making it worse, I think. And that's tacit programming or point-free programming. I think point-free is the more regular term for it. I didn't know tacit programming. I didn't know the word, but it was perfect with my curry it, and pipe it. Tacit. It's perfect. So I had to use that word. Yeah, so this is where we left off on the previous slide. It's exactly the same. Excuse me. The thing with point-free programming, points in this case mean arguments, function arguments. It's from mathematics, I believe, and it doesn't matter. So point-free programming sort of means removing function arguments. It means removing these pieces from our functions. There are two ways I think we can do this, by just removing these things and of course adapting our code to still make it work. And the other way is by using function composition, or changing our functions, wrapping our functions so that they so that we can in that way remove these the arguments. So the first thing is the easiest in this case. As you can see, this is a function that accepts a horse, and we pass it directly to the function that pipe returns. We don't do anything with it, so we can just remove this. It might take some practice to see it, but we can just remove it. We can just remove these characters and these characters, and we will have exactly the same result. So it's already I think better. We removed some wrapping code, some wrapping function. Yeah. The other way we can do this, because here we still have all these arguments we're mentioning. we can do that by just using curry, using a general curry method from, again, in this case, Ramda. There are more libraries that supply it. We can wrap an existing function that isn't curried, that accepts more than one parameter, and we can just curry it by passing it to a general curry function. It's a lot cleaner. Again, it requires some more abstraction. So it requires knowledge, like I said before. You need to know what curry means. That's the trade-off. But I think it's worth it if people invest a little in functional programming and practice a little bit with this. If we can all write this kind of amazing code. Yeah, I'm very excited about it, as you may notice. One final thing we can, so let's assume that paint and attach and feed. We assume we have those functions in our own in our control. We wrote those functions. We can also just query them immediately. We can also just write them immediately that they are queried. So that will remove the queried prefix in this case. We can just call them you can just call them paint or in attach and feed exactly like we want them, like this. And then we're at our final result. So we started with a more or less imperative piece of code with consts and in between variable assignment. And we ended up with I think a nice piece of declarative code, and of course a unicorn.